Chapter 6, Section 5, Trapezoidal Rule. This is the last section of Chapter 6. Page 316, Exercise 6, the integral of sine x dx from 0 to pi. In exercises 1 through 6, Part A used the trapezoidal rule with n equal to 4 to approximate the value of the integral. That's Part A. We'll do that, and then we'll read parts B and C. We start this problem with delta x equals b minus a over n. We used the same formula with the left rectangles and the right rectangles and the midpoint rectangles. Same, delta x equals b. This is b. A, this is a, over n. N is 4. Delta x equals pi over 4. B minus a over n. And just like with the rectangles, we're going to make a table with an x column starting at 0. This is what we change x by, and pi is where we end up in the table. So here's the table. X is starting at 0. Delta x is pi over 4. 0 plus pi over 4 is pi over 4. Pi over 4 plus pi over 4 is pi over 2. Pi over 2 plus pi over 4 is 3 pi over 4. And 3 pi over 4 plus pi over 4 is 4 pi over 4, which is pi. We stop at pi because it's integral from 0 to pi. Each y is equal to the sine of x. That's the integrand in this exercise. The sine of 0 is 0. The sine of pi over 4, I'm just going to write it like this, the sine of pi over 4. The sine of pi over 2 is 1. If I didn't know that, I could just write sine pi over 2 here. The sine of 3 pi over 4 is what I'm going to write in this spot. And the sine of pi is 0. I'm going to plot these points and not connect them. 0, 0, pi over 4, some number, pi over 2, 1, 3 pi over 4, some number, I have a feeling it's the same y that's there, and pi 0. So 0 to pi, this on the y-axis is 1. When we computed the left rectangle approximation method, we would make vertical lines and flat tops for left rectangles, and same for right rectangles. For trapezoidal rule, we make vertical lines from the x-axis to each of these points. So there's 1, 2, 3, 4, 5 vertical lines here. 2 of them are height 0, but theoretically there's 1, 2, 3, 4, 5 vertical lines here. and we just connect all of these dots with straight line segments, not the curve that we know y equals sine x is a curve, but we're going to make straight line segments. And what I tell you, what I tell myself, is these four geometric shapes are trapezoids. I realize the first one and the fourth one look like triangles, but we're still going to think of them as trapezoids. We're going to find the areas of these trapezoids and add them together. When we do that, when we add the areas of these trapezoids together, we will be approximating the integral of sine x dx from 0 to pi. We're going to say it's approximately equal to that's trapezoidal rule, subscript 4, meaning 1, 2, 3, 4 trapezoids, and the area of every trapezoid is 1/2 the height times base 1 plus base 2. This applies to each of these trapezoids. In this two special cases where they're really triangles, one of the bases will be 0, so that what will be left here will really be the area of a triangle, 1/2 height times base, because the other base will be 0 whenever these happen to be triangles. But you don't need to think about that. Just think of them as all trapezoids, where sometimes one of the bases is 0. So I'm going to write down the areas of these four trapezoids and add them all together. But since the height of every one of these is delta x, and the 1/2 will apply to each, we're going to factor that out. So we're going to have 1/2 the height. The height is the change in x. Right here, that's the height of each trapezoid. The height means the distance between the parallel sides. And that is pi over 4 for each trapezoid. So as I said, we're factoring that out. The sum of the bases for the first trapezoid are 0 from this table, 0 and the sine of pi over 4. So 0 plus the sine of pi over 4. Right there, those are the bases of the first trapezoid, which really is a triangle. Plus, now I need the bases of this second trapezoid. The bases are the sine of, this is the first base of the second trapezoid, and this is the second. So the bases of this are the sine of pi over 4 and 1. By the 1, I really mean the sine of pi over 2 from right there. And now we're up to the, so right here, those are the bases of the second trapezoid. Now I'm up to the third trapezoid, right here, this third trapezoid. The bases of that trapezoid are right here, that's the sine of pi over 2, which is 1, plus the other base of this trapezoid is the sine of 3 pi over 4. So there we go, those are the bases of the third trapezoid. And there's one more trapezoid, right here, this last one. That's the fourth one. The bases of that trapezoid are the sine of 3 pi over 4 and 0. And the 0 is really the sine of pi from the table. Right here, all this blue down here is showing that we're adding the areas of these four trapezoids. 1/2 the height, right out here, that applies to every trapezoid. And then we have the sum of the bases the sum of the bases, the sum of the bases, the sum of the bases. The bases are the parallel sides. So out front here we have pi over 8. I'm going to put all this in my calculator. Make sure I'm in radian mode. So in the calculator I'm putting in 0 plus the sine of pi over 4 plus the sine of pi over 4 plus 1 plus 1 plus the sine of 3 pi over 4 plus the sine of 3 pi over 4, and there's a plus 0 at the end. So just doing all this in the parentheses, I see 4.828427125. And when I multiply that by pi over 8, I get the answer I would write on the AP exam if this were that, 1.896. So here's a summary of Part A. Exercise 6, Part A. It says the integral of sine x dx from 0 to pi using a trapezoidal rule. This is approximately equal to, the approximation is called the trapezoidal approximation, subscript 4, and that came out to be about 1.896. Part B says use the concavity of the function to predict whether the approximation is an overestimate or an underestimate. So in general, if a function is concave up and we are estimating the area between that and the x-axis, when we use trapezoids to approximate, they go, in general, they go over the top of the actual curve. So for a concave up graph, concave up, trapezoidal approximation overestimates. If a graph has a concave down shape, and we're talking about the area between the curve and the x-axis, trapezoids, you can see here, would underestimate. They go under the curve when it's concave down. These trapezoids, they don't reach the whole curve. If a curve is concave down, the trapezoidal approximation will be an underestimate. See? Underestimate. Concave down, trapezoids underestimate. Concave up, trapezoids overestimate. So from this exercise, the sine graph between 0 and pi is concave down, that means 1.896 is an underestimate of the actual integral. Underestimate. In other words, it's an underestimate of the actual area between y equals sine x and the x-axis between 0 and pi. So that's part A. Your reason, to give a reason for this, you would just say because y equals sine x between 0 and pi is concave down. That's all. No other words. Part C. Find the integral's exact value to check your answer. The integral of sine x dx from 0 to pi is exactly cosine x evaluated from 0 to pi, whatever that means. Cosine x is the antiderivative. Actually, it's negative cosine x. The antiderivative of sine x is negative cosine x. It's easy to get these confused with derivatives. So by the fundamental theorem of calculus, this integral, this definite integral, is equal to negative cosine pi minus negative cosine 0. And the cosine of pi is negative 1. This says negative 1. The cosine of 0 is 1. This says negative, so that's plus 1. And that means the exact value of this integral is really 2. And as we said, 1.896 is close to 2, but it's an underestimate. The end.